So this is gonna be the uh, 9.1 video, right? So the image you're seeing here, you have the four fundamental forces of the universe, right? So they're called the strong force, the electromagnetic force, the weak force, and the gravitational force. All right, and you've learned two of these before, right? The electromagnetic force, right? Electric fields, magnetic fields, and you learned about the gravitational force. All right, I'm going to introduce to you the strong and weak force, and you'll see here that the strong force, if you look at the strengths of each of these forces, that the strong force is the most, is the strongest force, with the electromagnetic force coming in second, and the weak force third, and finally the gravitational force is the weakest force out of them all. And so now we're going to go into something called quarks. Now in chemistry, you learned about protons and neutrons, right? So protons are positively charged, and neutrons are neutral, right? They don't have no charge, and so a proton is made up of two up quarks, right? Something called two up quarks. You'll let's just start with the fact that protons and neutrons are made up of quarks. All right, so both protons and neutrons are made up of three quarks each. Yes, there is something smaller than something that makes up a proton. On the other hand, there's nothing that actually makes up an electron. So protons and neutrons are made up of three quarks each, and they interact via the strong force. Right, this is something that's important to remember. They interact with each other through the strong force. So you have this practice problem here was the total number of quarks in a helium nucleus, consisting of two protons and two neutrons, right? So here you have this, right? So if you know a proton has three quarks, right? So one proton has three quarks, and one neutron has three quarks as well. Well, if you can do the math, right, two protons would have six quarks, and two neutrons would also have six quarks. Well, then you'd have 12 quarks in total. All right, and so that's the answer. So on your reference table, you'll see on the third page, you'll see all the quarks of the Standard Model. So up quarks, if you look at the top here, up quarks have a charge of positive 2/3 E, E representing elementary charges. Same thing with charm and top, and down has a charge of negative 1/3 E. Right, so down quark is abbreviated by the letter D, strange by the letter S, and bottom by the letter B. And they all have negative 1/3 E on the bottom here, bottom half. And if we look at this a bit closer, more closely, you'll see that a proton is made up of two up quarks, right, and one down quark. Well, how does that work? And let's take this, right. So you'll see here that a proton is made of two up quarks, one down quark. Well, an up quark, as referenced on your reference table, well, an up quark has a charge of positive 2/3 E. Right? And a down quark has a charge of negative 1/3 E. And so if you add up all these charges, positive 2/3 plus positive 2/3 and minus negative 1/3, you get a charge of positive 1 E, which is the charge of a proton. And likewise, you expect that, well, if you add an up quark for a neutron, rather, you'd expect, well, one up quark, positive 2/3, one down, negative 1/3 E, another down, negative 1/3 E. Well, if you add up all their charges, right, and then you get 0. And that's the charge of your particle, of your neutron. And then it's important to remember the composition of a proton and a neutron. So a top quark has an approximate charge of what? So there's an easy way to solve this without math. You realize that top quark has a charge of, as it says on your reference table, has a charge of positive 2/3 E right here. And so a top quark has a charge of positive 2/3 E. which means that you cannot, well, two of these choices are automatically incorrect, right? You can't have a negative charge if you're positive. And a top quark has a charge of positive 2/z, which means it's less than 1. And if 1e is 1.6, well, the only... hold on, I crossed out the that thing right there. It's not A or B. Well, again, it's positive 2/3 e. The top quark has a charge of positive 2/3 e, which is less than 1. And if we know that 1e is 1.6, well, if something less than 1, well, it has to be C, choice C, right? 1.07. Alternatively, you could just have done this through math. So you have positive 2/3 e multiplied by 1.6 times 10 to the negative 19, and you'll get the letter C as your answer. So here we have the three, again, all up charmed top quarks all have a charge of positive 2/3 e, and down strange bottom all have a charge of negative 1/3 e. So a particle unaffected by an electric field could have a quark composition of what? So here we get to, again, we're using our reference table for this. Now the question, when it says unaffected by the electric field, that means they're looking for a neutral charge. So you're looking for a choice that gives you 0, a charge of 0. And this question is kind of easy because the answer is the first choice, CSS. What does that mean? Well, it's charm. And if you look at your reference table, a charm quark has a charge of positive 2/3 e, and a strange quark has a charge of negative 1/3 e, and another strange quark has a charge of negative 1/3 e. And so if you add up all these charges, you're going to get 0. Same thing with BBB. If you just do it for just to show you what you would get, right? So BBB would give you a charge of negative 1 e. UDC, up down charm, would get you a charge of positive 1 e. If you add them all up up down would also be a charge of positive 1 e. Up down being a proton, right? Being a proton. And this video you can watch yourself, but the gist of the video is that there's something called antimatter. Now you might have watched this in sci-fi movies about this. It's kind of like the special thing. Unfortunately, antimatter is actually just matter, but the opposite version. Well, what do I mean by opposite? Well, everything is the same, first of all, right? Your mass is the same. Your energy is the same. The only difference is that antimatter has the opposite charge of regular matter. All right, so an up quark would have a charge of positive 2/3 e, and well, what about an anti-up quark? Right, an anti-up quark would have a charge of negative 2/3 e, right? And we would denote the symbol antimatter with the bar over it. So if up quark is positive 2/3 e, then an anti-up quark would have a charge of negative 2/3 e. And you'll see this on your reference table. Your reference table down here says that, well, for each particle, there is a corresponding antiparticle with a charge opposite that of its associated particle, right? And so if we look at this, look up here, this image, right? We have hydrogen and anti-hydrogen. So in the middle, you have an antiproton, and in the anti-hydrogen version, you have something called an antiproton, right? And the charge of a proton would be positive 1 e, and an antiproton would have a charge of, we can't see that quite clearly, it has a charge of negative 1 e. So it's essentially everything is the same mass, same energy, just different charge. An electron is the same thing, right? Electron would have a charge of negative 1 e, and something called a positron, right? The antimatter version of electron would have a charge of positive 1 e. Right? Electron would have a charge of negative 1 e. Positron would have a charge of positive 1 e. And if you guys think about it, we do use antimatter in real life. They're called PET scans, right? They're used in the medical field. That's how certain things are imaged. They shoot out positrons. So the same thing. Protons have two up quarks, one down quark. Antiprotons are the opposite, so they have two anti-up quarks and one anti-down quark. And again, why don't you see actual antimatter in real life? Well, it's because if antimatter were to ever come in contact with matter, they would annihilate each other and give off energy. And just turns out the universe just has a lot more matter for some reason, which we don't understand why. So let's take a further look at your third page of your referencing. We're focusing on the third page, classification of matter on the left-hand side over here, and on this left-hand side, classification of matter. So matter is broken down into two separate categories, right? Something called hadrons and something called leptons. And we're going to focus on the leptons first. So leptons are particles that don't interact via the strong nuclear force, but they interact via the weak force. All right, so first off, right away, you should remember that if you're looking at this part of your reference table, that you're going to classify leptons as something we call, they interact via the weak force. All right, so leptons, weak force. And the leptons are labeled on your reference table. So electrons are something we call leptons, the muons, taus, etc., neutrinos. And hadrons, on the other hand, are nuclear particles that interact via the strong nuclear force. And so on the other side, you have hadrons, and they interact via the strong force. All right. And now we're going to break down hadrons, right? We can break down hadrons into something called baryons and something called mesons. And we're going to first cover baryons. So baryons, as it says on your reference table, a baryon is made up of 3 quarks. Right? So baryons can be protons or neutrons. And antibaryons are antiprotons and antineutrons. So again, the most important thing here is, well, baryons consist of 3 quarks or 3 antiquarks. 3 antiquarks being the antibaryons. And it's on your reference table. Now, mesons, on the other hand, are a quark-antiquark pair, as it also says on your reference table, right? They give you a clear path. It's a quark and antiquark pair. And charges on a meson, they range from -1e to +1e. Right? So -1e, 0, or +1e. Those are the charges. You can't have more than -1e, and you can't have more than +1e. So according to the standard model of physics, a neutrino is a type of what? It's a type of lepton, as you can see on your reference table, right? So if you go here, you'll see here, electron is what we call a lepton. Or rather, a neutrino. A neutrino is what we call a lepton. Baryons may have charges of what? Again, baryons are either protons or neutrons or antiprotons or antineutrons, right? And they all have set charges, -1e, +1e, or 0. So it's going to be C, right? Nothing else makes sense. You can't really have more than +1e or -1e here. A meson could be composed of what? Again, you're looking for a quark and anti-quark pair. It is going to be C, a strange quark and an anti-charm quark. It is not B because electrons are leptons, right? There's something called leptons. Yes, there's a particle version and anti-particle version, but these are classified as leptons. So the answer here is C. A meson may not have a charge of what? Again, I give you the ranges of a meson right here. Charges range from -1e to +1e. Therefore, The only charge that does not make sense is going to be B here, positive 2e. All right.